Hello, everyone. You are welcome to today's lesson. And today's lesson will be lesson 2 of the topic of calculus, but we are looking at differentiation. Okay, you know, calculus is in 2 parts, differentiation and integration. So we are looking at the first part. So in our previous meeting, which was the lesson 1, okay, we looked at limits of functions, okay, and differentiation from the first principle. So we ended at the differentiation, okay, from the first principle. And this was the last set of questions that we saw. In fact, the first set of questions anyway, okay, but I asked you to do V as your assignment, okay, and once we are able to do that, or we did, it was the V, right? Yeah, I think so. It was the V. And once you're able to do V, you should be able to do VI. Okay, so quickly, let's move on to our next set of questions. Again, we are still looking at differentiation from the first principle. Okay, usually the functions will come in different forms. So you have to know your strategy, okay, and the best way or the ideal way to deal with what the function in terms of first principle differentiation. Okay, so this time around, unlike the first situation, if you go back, you can see that our functions were pretty, no denominators. Okay, we were dealing with polynomials, but this time around, we are going to deal with rational functions. If you look at the function that we have here. Okay, rational function basically will mean that you will do a little more work. Okay, but remember, the concept basically will be the same. So this is what we are going to do in terms of the solution presentation. What do we do? Solution questions are numbered because your solution must be numbered as well. So question number 2, solution number 2. Okay, then A. We need to, so underline, differentiate from the first principle. Very critical. Okay, so here, if you fail to differentiate using the first principle, you know, okay, you will not score any marks. Okay, so you have to adhere, okay, strictly to the instruction. So giving A, f of x is equal to 3 over x. Okay, now what do we have? Forgive me. So here we know we have to quote the first principle. And I've told you it's not, okay, named after anyone. So you can go ahead and quote it. I can write, but, okay, my f prime of x, because I was given f of x. So the differential of that will be f prime of x will be equal to the limit as h approaches 0 of what? My f of x plus h minus f of x all over the whole of this over, okay, h, take note. So in this case, we need our f of x, which thankfully is given, is known. Then once we know f of x, we can find f of x plus h. Okay, so I can go and write, okay, this implies that my f of x plus h will be equal to, okay, 3 over x plus h. Do you agree?
Yes, please.
Okay, so now what do we do? It means we can now substitute our parameters. So we are going to write, okay, I can draw my conclusion here, remember, when you are going to carry out substitution. So therefore, f prime of x, okay, which will be the first derivative of f of x, will be equal to the limit as h approaches 0 of what? F of x plus h, which is not a pretty function, is 3 over x plus h, don't worry, minus your f of x, and f of x is 3 over x. But don't forget, it's the whole of this one over h. Am I clear? Hello, is my point well made? Okay, so
Yes.
at this point, obviously, once we see fractions, it implies that, okay, a little more work will come. So what you have to do is go and write your numerator as a single fraction. Okay, your numerator. And as you are writing your numerator as a single fraction, remember, your limit is there. It cannot go at this point. Okay, then we are going to get your LCM for the numerator will be x into x plus h. Do you agree? So you ask yourself, okay, x plus h will go into this how many times? And it will go into our LCM x times 3. So it will be 3x. Then minus x will go into our denominator, the LCM, how many times? It will be s plus h times and times 3. So it will be 3 into x, okay, plus h. But don't forget, it's the whole of that one divided by what? H. Okay, so I'm going to write divided by h. Now that's my numerator, denominator, everything is a single fraction. Okay, I can change the bar to the symbol and move on this bar here to the symbol. So in effect, as you mature, okay, you can move from where you have here to this particular step, or you can change this one to multiplication straight away. So going forward, I will do that. Okay, so this gives me my denominator will be the x plus h, sorry, into x plus h. Then my numerator, I will go and expand, combine like terms if any. So 3x minus 3x, then minus 3h. Okay, the whole of that times 1 over h. Do you agree? Hello, my professors, are you following? Okay, so if you are with me up to this point, we thank God. So this will be equal to still your limit as h, okay, approaches 0 of what? Okay, so you now go and have this. Okay, your denominator will now be, okay, x times h. Okay, so maybe h, x, then into x plus h. Then your numerator will be this will, and this will cancel. So I'll get minus 3h. Is that clear? Is my point well made, my professors? Okay, so at this point, you know, we can equally reduce that. So the h here will cancel the h that. So in effect, we are going to get the limit, so equal to the limit as h approaches 0 of what? Of minus 3 over x into x plus h. Okay, so at this point, okay, we can carry out substitution in the denominators to see whether it is allowed. If h is equal to 0, you get x into x plus 0, so it will be x into x. So the denominator will not give you 0. So we can carry out the substitution. So as you are substituting, the limit must go at that particular point. So you have minus 3 over x into x plus what? 0, because h, okay, is approaching 0. So it will be 0. So that gives us minus 3 over x times x, which is what? X squared. You let me write it just for the purposes of explanation for the first question on the fraction. So minus 3 over x squared. So this becomes, okay, your result in terms of the differentiation from the first principle. So it means if you differentiate that function there, this should be your result. Is my point well made? Hello, is my point well made? Very good. Okay, so we are going to do maybe, okay, one more. So I will go forward and guide you. Okay, so let's come and look at, I'll pick this. If you're able to do this, okay, then indirectly, we are able to do all that we have there. Or better still, if you're able to do this, you should be able to do the rest. So I'm going to pick the E, and as a guide, you use it to do, okay, the rest. Okay, all right, so now let's look at the E. E, what are we giving? We've been giving f of x, okay, I wish maybe it was y, so that we'll use y. It's equal to, but it doesn't mean anything. Okay, you know, 3 over x, okay, plus y, oh sorry, plus x squared. Okay, so take note. So with this one, what are we supposed to do? We quote, is that not it? And when you are quoting, you can choose to write that or not, only that I usually write but. Okay, so in this case, I will write but. I'm putting a formula. Okay, but before you put your formula, this is the advice. Okay, anytime a function is given and you realize that the function came, okay, in the form of a partial fraction, not a single fraction, take it to your comfort zone. Okay, working with a single fraction will always be better. So every fraction which is in parts, partial fraction, you can always take it to its corresponding single fraction. Okay, so here before I even come and put the rule or the formula, please, I will write my function because I know my plan. Out of experience, I know that it will be better if I change the function which came in partial fraction to a single fraction before I even write my part or quote the formula. So that is what I'm equally going to do here. Now that you have this advice, I expect you to do the same. So at this point, what are we going to get? We are going to write what we have here to be equal to your f of x. You are transforming it, you are taking it to your comfort zone, which is a single fraction. So if I take my LCM will be x. Do you agree? Then my numerator will give me x will go into x how many times? 1 times 3. So I'll get 3. Okay, then plus this is over 1. Okay, 1 will go into x how many times? It will be x, okay, times. Okay, then times x squared, and that will give us s cubed. Is my point well made? Hello, is my point well made? My professors, are you there?
Yes, please.
Okay, all right, so now you can quote. Okay, so I'll write but because the function is in the form that you like. So but my f prime of x, because I was given f and I'm asked to differentiate, I will end up getting f prime of x. And that will be equal to the limit, okay, as h approaches 0 of what? F of x plus h minus what? F of x all over, okay, h. Okay, so at this point, we know f of x, so we have to go and find f of x plus h. Someone who is matured and equally knows, okay, the stuff, you know, after getting f of x here, okay, the person who can move and straight away, right, this implies that f of x plus h will be equal to, because you know you will need it. Okay, so now, if you didn't know and you have done this, if you put the formula will tell you that you need it. So you can still go and find it. Okay, so in this case, I will write, okay, f of x plus h, okay, will be equal to wherever I see x in f of x, which is now what I have here. Okay, I substitute s plus h there. So I will get 3 plus x plus h, okay, q all over, okay, s plus h. Do you agree? My professors, are you with me? Okay, great. Okay, so now this is what we are supposed to do. And remember, I told you, okay, if possible, do all your expansions here before you go and substitute, if possible. After maybe later, I will give you a certain advice. Maybe per experience, you can equally advise yourself. So what are we going to get? Okay, let me see. What do we have there? So we are going to expand the numerator, and we should all be able to expand this mentally, okay, because we've all done binomial theorem. Okay, so we are going to have that one expanded mentally. So let's go and have s plus h. Okay, then. So my f of x plus h will be equal to, we said it will be 3, okay, plus, as for your denominator, little or no work. Okay, so the denominator gave us what? The denominator is x, right? Plus h. Okay, so your numerator, x plus h cubed, will give you s cubed okay, plus 3, okay, x, okay, squared h, okay, plus, okay, 3x squared, then plus h cubed. Do you agree? Do you agree? Okay, so the Pascal coefficient will be 1331. Okay, and the powers of the x will be decreasing, whilst that of the h will be increasing. So this is what we have. After expansion, can you see any? Please don't write, hold on. Okay, I'll give you another, or if you want to capture, hold on. Okay, we'll have another approach and we'll see which one will be ideal. Okay, then later you can write. Okay, so after expansion, do we have any like terms? No. So we can now go and substitute. So let's see what is going to happen. So therefore, your f prime of x will be equal to, remember we said the limit as h approaches 0 of what? F of s plus h, which is the whole of this. So I'm going to write it, okay, 3 plus x cubed plus 3x squared h plus 3x squared plus h cubed all over. This is it for only f of s plus h. Okay, all over this, then minus f of x, which is what? F of s gave us what? The single fraction form. Okay, so that gave us what? 3 plus s cubed over x. You could have even made that determination. So 3 plus x cubed over x. But remember, that is not all. The whole of that one divided by h. So I don't want to write all over h. Okay, so I will put this in brackets and write, okay, times 1 over h. Is that clear? Failure to put the whole of that in brackets will be costly because we are not dealing with a single fraction. So now let's see what is going to happen. Again, you come and take the, so write this as a single fraction. Okay, so we are going to get this to be equal to, the limit will still be there as h approaches 0 of what? Your LCM is going to be x plus h, okay, times x. Okay, but you still have h there. Later you multiply. Okay, so times 1 over h will come. Or as you mature, you can add that. But let's deal with this one first before we come and deal with the 1 over h. So this as a single fraction, we are dealing with what we have in brackets. Okay, this will go into this x times. So it will be x times all the terms here. So that will give us 3x, okay, plus x to the power 4. Are you following? Plus 3x cubed h plus 3x, okay, squared h squared, then plus x h cubed. My professors, are you following? Hello, you are too quiet this morning for my liking. Are you following?
Yes,
Yes.
Okay, then minus, okay, x will go into this s plus h times, then times the numerator here. So that one you have to put both binomials in brackets. So 3 plus x cubed times what? X, okay, plus what? H. Okay, the whole of that times 1 over h. All correct. Is my point well made? Hello, is my point well made, my professors? Okay, all right.
Yes,
So at this point, this is what we are going to do. So you expand this one, then combine like terms and move on. That is one approach. Okay, I don't want to even continue. Now let's go and look at another approach. Hold on. Okay, so we'll start. Again, we are going to start the same way as we started over here. write this as a single fraction. Okay, then after that, this is what you do. Anytime you are dealing with a fraction and you are differentiating from the first principle, please, let's see what we are going to do. You can see that the first one, we expanded directly, okay, before carrying out our substitution. This time around, we want to see whether direct substitution without expansion will be critical or will be useful. Okay, so let's go and do that, okay, over there. So on that note, I'm going to continue from therefore, I'm going to carry out the substitution. I will not expand this. I hope you get my point. I don't want us to, okay, waste time. So this will continue. Now I'm looking at the other alternative. Okay, so therefore, now f prime of x will be equal to the limit as h approaches 0 of what? F of s plus h. And that gives us, okay, this fraction, okay, that is a little prettier than its expanded version. That is the 3 plus s plus h cubed all over s plus h. So we are going to do that. So it will be 3 plus x plus h, okay, cube all over x plus h. Then minus, okay, remember that one gave us what? 3 plus what? X cubed all over, okay, x. Okay, so now the whole of this one over h. Do you agree? Even at this point, you could have written the whole of this in bracket times 1 over h or divided by h. Please, are you with me? Hello, if you are with me, respond.
Yes, please.
Okay, great. Okay, so now this is what we are going to get. So you can see that the rest is basically algebra. I've told you relative math, apart from the principle, okay, the rest is just your algebra. So your algebra needs to be strong. Okay, so what do we have? We are going to have the limit as h approaches 0 of what now? The single fraction of the numerator. And that will give you, okay, this. LCM will be x, okay, into x plus h. Okay, and this one you are going to get, this will go into this how many times? We are going to get, okay, let's see what is going to happen. So this will go here how many times? X times, so times this. So indirectly, you are going to get what? 3x, let me write it for the purposes of explanation. Okay, so that when you see it, you can easily relate. So x here, but that's not all, times 3 plus x plus h, or q. So it means this in actual fact should be the square bracket. But that's not all. You are not done with your numerator. Then you are going to get what? Your x will go into this how many times? And that will give us minus, okay, your 3 plus s cubed times what? Your x plus h. Okay, the whole of this one times what? Okay, 1 over h. All correct. Is my point well made?
Yes, please.
Okay, so now let's see what is going to happen. Okay, at this point, okay, let me see. The work is becoming, so I have to move on to the next page. I wish maybe if someone has it, I'll rely on you to provide. I don't want to be moving. Okay, so let me quickly, okay, continue here, see if I can continue here because I don't want to be moving. So I'm going to get the limit. This is equal to the limit as h approaches 0. Okay, it's just the algebra. Okay, so now what do we get? It will be 3x. We are removing the bracket, the square bracket, okay, plus x into what? X plus h cubed. Okay, then minus, now we are going to get 3 times x. So that will give me 3x. I hope you are with me. Then minus 3 times h, that will give me minus 3h, then minus x cubed times h, and that will give you minus what? S cubed h. Okay, unfortunately, there will be a term, so plus 3h. So it will be minus 3h, sorry. Okay, all over. Now my LCM h will come in, so it will be h times x, then times what? X plus h. All correct. Is my point well made? Okay, so let me see. Okay, all right. So at this point, okay, this is what we are going to do. We are going to have this to be equal to, let's go. The limit as h approaches was 0 of, you know that this and this will go, am I right?
Yes, please.
Okay, that will go. So your numerator, do you have any other term that will vanish? Okay, so on that note, we are going to get, okay, x into x plus h cubed, then minus 3h, okay, minus x cubed h, then minus, oh, this one, was it 3h? Was this one also 3h? Let me see. This one was 3x, then 3h, so it's not 3h, it's 3x. Is that clear? No, I've done the 3x. Let me see the minus 3x minus 3h. Okay, then x cubed. So this will be x to the power 4. Right? Minus x to the power 4, then minus x cubed h. So what happened? And you didn't draw my attention to that. Do you get the point? Okay, so the last two terms here wrong. Are you with me now? And no one had my attention drawn to that. Okay, it wasn't intentional though. But sometimes as you mature, as you move on, you realize that there is something wrong. Okay, so minus 3x, okay, minus 3h, it is here. Okay, minus s cubed times x, so that will give us minus s to the power 4. So I've done the minus s to the power 4. Okay, then minus x cubed times h, so okay, minus s cubed h. Point well made. So it means, okay, we need to go and write our terms, okay, out clearly. So 3x, okay, this is supposed to be 3x. Okay, have you catered for that? No. All right, so please watch my back if, okay, I have, so that you can, so let me clear the whole of this. So minus 3x. Okay, I think that is gone. The 3x is gone. Okay, so it will rather be this, okay, minus 3h. Then minus what? X to the power 4. Then minus x cubed h. Okay, all over, okay, hx, x plus h. Okay, so now at this point, let me pause and let me see how you can be practical in terms of your thinking. Okay, so anytime you have an algebraic fraction, before you can reduce, both numerator and denominator must be in the factorized form. Okay, the denominator is in its factorized form. Do you agree?
Yes, please.
Okay, by the numerator, obviously it's not. Okay, because for you to see factors, we have to see only brackets, sort of. So in this case, whether you like it or not, you have to expand the x plus h cubed, either from the beginning or at this point. Is my point well made? Because you have to expand, combine like terms and check if you can do your factorization. So at this point, we are going to do the expansion. So we'll see. Like I said, per experience, you know which one will be ideal. So we are going to get x out. Okay, usually I'll write what needs little or no effort, which is my denominator in this situation. So I'll write that one, waiting for my numerator. So if I expand this, remember we said we get s cubed plus 3x, okay, squared h plus 3x h squared, then plus h cubed. Okay, that's it for only the expansion. I could have multiplied through straight away. Okay, so then, but I want to do it systematically for you to follow. So you are not done. Then minus 3h, okay, minus x to the power 4, then minus s cubed h. Is my point well made? So this is what I want you to do. Now go and expand, multiply through by the x. So you get s to the power 4, 3s cubed h, 3s squared h squared, then x h cubed. Then see whether after that you have like terms to deal with, because you can see subtraction here. And here all your terms will be positive. So if you have any like term here, it's likely it will go. Okay, so expand, and let me see whether I created the next page. Okay, I did. Okay, so expand, I'm waiting. So still I'm dealing with, therefore, f prime of x will be equal to the limit as h approaches 0 of my denominator is x, h into x plus what? Okay, h. This is what we have. Now, if you look at the numerator, we are going to do it mentally and deal with the one that will go. S cube. Okay, do I have any s cube here, term here? Sorry, s to the power 4, forgive me. S to the power 4, because with this times this, s to the power 4. You can see that you get minus s to the power 4. That will cancel that. Is that clear? Hello, are you with me?
Yes, please.
Okay, then we come to this, and this will multiply and give you 3s squared h. There is no s squared h term here. So it means I need to go and write that, because nothing will combine with it. So I'm going to equally write that. So let's go and do that. That is 3s cubed what? H. So I'll write 3x cubed h. Okay, now let's go to the next terms. Oops. Okay, the next terms, what do we have? X times this will give us 3s squared h squared. Do you have any s squared h squared term here? No. So you have to equally write that. Is my point well made?
Yes, please.
Okay, so we are, no, did we do this? Yes, we did this, and this will give us 3s cubed h. There is s cubed h term here. Can you see it? So you have to be very critical how to identify your like terms. So it means 3s cubed h minus s cubed h will give us 2s cubed h. Is that clear? So plus 2s cubed h. Okay, so let's move on to the next one.
Mr. Hackman,
Yes, please.
please, we wrote 3x cubed h.
We wrote it.
Yeah.
Where?
Like, we didn't see the x cubed h at the end. So
You didn't see this one?
No, I'm saying that, no, like, what you just wrote right now.
Oh, I wrote 3 instead of 2.
They have already written 3x squared h.
Ah, let me see. Oops. Okay, instead of the 2. Okay, I get you now. So that one has a like term. Okay, so we need to deal with that. Okay, so initially, I think I get your point now. So it's rather this that must change to 2, right? Okay, so let's do the combination together because I'm moving. Okay, so 2s cubed h. So now it means the s cubed h term catered for. Let's go and look at the other terms. So the other term will be s to the power 4. Okay, will you get any s to the power 4 term? So s to the power 4 is gone. So it means let me cancel the ones that are gone. So this and this gone. Is that not it? Oops. Is that not it? So that I don't go and stress myself again. But you know, you will expand. Okay, you can expand so that you can clearly see, okay, what you have there. I want to skip. Okay, that's a more reason why. But if I had expanded because of the digital marker and the space. Okay, so this is what you expand and combine. First principle questions, especially when you contain fraction, is basically to play with your algebra, is to expose your algebra. So if your algebra is not strong, okay, you won't find it interesting at all. So in this case, we are going to get, we've dealt with the s to the power 4, then the s cubed. The next one will give us 3s squared h squared. Do we have any s squared h squared there? No. So we are going to write that 3s squared h squared. So that will be our next term of interest, plus 3s squared h squared. Okay, then let's move on to the next one. Oops, I'm supposed to go back. So we've done s squared, a squared, then plus x h cubed. Okay, so do we have any x h cubed term there? No. Okay, so we are going to write that, and after that, this term is standing. That's the 3 minus 3h. Okay, standing, so write it. So we are going to write the x, okay, h cubed, okay, there. So let's go and write that as our next term of interest. Okay, x plus x h cubed, then minus 3h. Okay, all over this. So at this point, direct substitution is not allowed. Okay, it's just because of the h. So we will manipulate by factorizing h in the numerator. Okay, so that gives us what? H out, okay, into 2s cubed, okay, plus what? 3x squared h, okay, then plus s h squared, then minus 3 all over your h into, so 8 times x times s plus h. Is that clear? I hope you are following me. Okay,
Yes,
so
please.
the h now will cancel. It's the algebra, but don't be confused. And once you know how to expand, how to combine like terms, okay, you shouldn't have any issues. So this will give us the limit as h approaches 0 of what? Now you are going to get 2x cubed plus 3x squared h plus x h squared minus 3 all over, okay, x into x plus h. Okay, so now direct substitution is allowed because if you substitute, your denominator will not be 0. Okay, so once I'm going to substitute, the limit goes. So I will get 2s cubed plus 3 into 0 squared. Oh, this one is x. Okay, so forgive me. It's s squared, oops. X squared h. Okay, so it's the h that should take the 0 in this stead. Okay, so now we have, let me write this one. This one is s squared h. Let me write my s squared. Okay, so I'm going to get s squared into 0, then plus what? X into 0 squared, then minus 3 all over, okay, your x into x plus 0. You are substituting 0 for h. So you get 2x cubed. This will go minus 3 all over, okay, x squared. Do you agree? Hello, do you agree?
Yes, please.
Okay, however, please always let the nature of the given function guide you to leave your final answer. If you look at the original function was partial fraction, only that you took it to single fraction. So because you took it to single fraction, it's most likely your result will be, after all your manipulations, will be in terms of what? In terms of a single fraction. Okay, however, the function didn't come in a single fraction form. So what you are supposed to do is take it back to its partial fraction. So by then, okay, by that, I mean that this will be the same as this step that I'm writing is basically for explanation purposes. As you mature, you can move straight to the answer that I'm going to write. So this one will cancel. So we are going to get what? Hey, I'm waiting. You get 2x, am I right? Then minus 3 over x squared. Is that clear?
Yes.
Okay, very good. So let me see whether, okay. Okay, all right. So, Kobe, Prof. Kobe, this is my advice. Anytime you have an algebraic expression, okay, and there is a term that is positive, never start with a negative term. It is ideal to always start with a positive term if there is a positive term, unless maybe you are told that leave it in a particular. Otherwise, algebraic expression, okay, must always start with a positive. Okay, take note of that. So that gives us what the answer that we have here. So if it's fraction, you should know that there will be a little more work. Now let's go and look at our next set of questions. Okay, so this time around, let's see. You can see powers. Okay, from the first principle. What do we do in dealing with this? So I'll just do the first one, guide you. Okay, and with that, you should be able to deal with the rest. Okay, all right. So now let's go and look at the solution quickly. Okay, first principle usually takes time because of the algebra involved. Okay, so question 3A again. Okay, first principles. Okay, so what do I have? Given y is equal to, okay, I needed y, so now I have y. All right, so now let me see. Prof. Kobe, what will you do in this situation in terms of the first principle?
Okay, so first of all, I'll represent y with f of x.
Okay.
Then for the function x plus 3 all square, I'll make it x plus h plus 3 all square. Then I continue from there, differentiated by first principles.
Okay, good. Okay, however, this is my advice. Anytime a function is given, okay, and you realize that that function, you can easily expand before you go and do, so manipulate, work on the functional. It's just like the other one that was a partial fraction. You work on it, you take it to single fraction. By so doing, it makes your work, okay, easy to deal with. Okay, so with this one too, if you can easily expand, and work with the expanded version. Okay, so by that, this is what I mean. So with this one, I need to transform this before I go and put. Okay, so in this case, I'm going to, per experience, I know that this expands to what? S squared here plus what? 6x, okay, then plus what? Okay, 9, am I right? So we've expanded, we want to see what will happen. So at this point, I will put, it's later that I will know that I will need f, but per experience, you know you need f of x and therefore f of x plus h. But I will put, so, but my first principle, so in actual fact, this implies that y is equal to this. Okay, so my first principle, I have the limit as h approaches 0 of what? F of x plus h, okay, minus f of x all over h. So now I don't know f of x, so I will let, okay, f of x be equal to y. And y is what? Now I will use this s squared plus 6x, okay, plus what? 9. So in effect, I'm going to get, this implies that my f of x plus h will be equal to, wherever I see x in the f of x, okay, I put x plus h there. So it will be s plus h, okay, squared, okay, then plus what? 6x, okay, plus h, okay, then plus what? Your 9. Okay, and remember, this one does not contain a denominator. It's not a fraction. So my previous advice, okay, holds. Okay, even that advice, it holds for all situations. Expand before you substitute. Expand before you substitute. You can do it. The other one, you could have done that. I remember we later came to expand anyway. Definitely you have to expand. Okay, so in this case, this is what we do. We are going to get the expanded version. Okay, so that gives us s squared plus 2xh, then plus a squared, then plus was 6x plus 6h, then plus 9. All correct. Is my point well made? Okay, so now what do we have? We are going to get this. So you expand and check if you have like terms. Can you see any like terms? Okay, so no, sort of. So now we can go and write therefore, okay, your dy, the first principle, I didn't quote it well. It's supposed to be dy dx. So if this happens to you, please, okay, don't cancel. You can come and write the dy dx. It's the same thing. If a is equal to b, b is equal to a. So that's, I mean, a way of being smart. Maybe it's a way of God trying to talk to me, okay, to you. Okay, I don't know how I put this one this way. So when this happens to you to do this, is that clear? Don't go and cancel it. It's the same. So now I will come and write my dy dx, okay, is equal to, then I go and substitute. So I'll get my limit as h approaches 0 of what? F of s plus h, which is the whole of this lengthy stuff. So x squared plus 2xh plus what? A squared plus 6x plus 6h plus 9, then minus all the terms here. So it will be minus s squared minus 6x minus 9 all over. Okay, so my h. Okay, so that's what I have. So in effect, I'm going to go, this and this will go. Minus 6x and this positive 6x will go. Then minus 9 and the positive 9 here will go. Is my point well made? So in effect, we are going to get this term, which is what? The limit, don't forget the limit, never, as h approaches 0, okay, of 2xh, okay, then plus what? H squared, okay, plus what? 6h, okay, all over h. Direct substitution is not allowed, so it means you have to factor out the h. So h in the numerator will come out 2x plus h, then plus 6 all over what? Over h. So this cancels that. So in effect, we are going to get that to be equal to. My professors, are you following? Okay, you get what? 2x plus h, then plus 6. You put the whole of that in brackets if you cherish marks. So h you can substitute, so it give you 2x plus 0 plus 6, which in effect will give us what? 2x plus what? 6. Okay, because what you have here was in the factorized form. Okay, you equally come and factorize if possible. Is that clear? So always let the nature of the function that you are asked to differentiate guide you in leaving your final answer. So if it comes in stated in the factorized form, your results, okay, you expanded. So it means if you deal with it, you end up getting an expanded version. There wouldn't be any bracket. So after that, you check your expanded version if you can take it to the original form, which is the factorized version. Okay, and the other one to partial fraction, you take it to single fraction, your result will end up being a single fraction. So because the function came by way of what? A partial fraction, you equally take it towards partial fraction. So it's the same point, okay, the same situation. However, when differentiating this from the first principle, you have to be very careful, a little careful. So let me see if you have space. Okay, we'll do the together. Okay, then after that, I think I will only go and guide you to deal with the rest in terms of the first principle. I won't do it together with you. Okay, so now what do we have? F of x is equal to what? Root of what? Root of x. So in this case, this is what we are going to do. You quote, okay, so, but my f prime of x will be equal to what? The limit as h approaches 0 of what? F of x plus h, okay, minus f of x. By now, you've quoted the formula a lot that it should stick. Okay, so all over h. So now you need f of x plus h. So I'll write f of x plus h, okay, will be equal to root of x plus h. Okay, so therefore, my f prime of x will be equal to the limit as h approaches 0 of what? F of x plus h is x plus h root of that minus f of x is root of x all over what? Over h. Okay. Is direct substitution allowed? Hello, is direct substitution allowed?
No, please.
No. So it calls for manipulation. So what sort of manipulation will you do here? Remember what we did yesterday? Any ideas? What sort of manipulation? Rationalization, remember. Okay, so it contains, so you rationalize, okay, so you multiply the numerator by root of x plus h plus root of x. But because you rationalize the numerator, you only expand what's the numerator, don't expand the denominator. So let's do it together and see. At a point, then I will leave. Okay, so lim h approaches 0. One of the questions, I think it was of this form, the limit question, because I wanted you to know how to deal with this. So let's see. We are going to get what? Root of x plus h, okay, minus root of x all over h, then times root of what? X plus h, okay, plus root of x all over root of x plus h, then plus root of x. So the numerator is what you rationalize. So you are going to, okay, expand that one and keep the denominator which you didn't rationalize. So that gives you h into, okay, root of what? X plus h minus plus root of what? X. Okay, your numerator will give you this one squared, root of x plus h all squared. Remember, conjugates will always expand into difference of two squares. So root of x all squared. My professors, are you following? Okay, so this question, it looks simple, okay, but the technicalities involved, okay, it's not that simple. Okay, so your denominator held constant, root of x plus h, okay, then plus root of x. Okay, your numerator, this, if you expand, will give you x plus h. Then this, if you remove the bracket, you expand, you are going to get minus x. All correct. So this will be equal to the x will go. So you get the limit as h approaches 0 of what? H over h into root of x plus h, then plus root of x. Okay, you close it, you extend this to cover. So this will be equal to, now you can do direct substitution. So indirectly you have the limit as h approaches 0 of 1 over root of x plus h, okay, plus what? Root of x. So you can substitute directly now. So 1 over root of x plus h, so it will be 0, then plus root of x. Okay, so this will give us what? Okay, 1 over 2 root of x. Am I right? Hello, is my point well made? My professors, are you there? Is my point well made? Okay, so on this note, okay, the next set of questions, I will only guide you. This is a single fraction. Okay, so you thank God. Okay, you deal with it in that form. Okay, you work with a single fraction if possible. Okay, then the next one, the same, so this will be the solution slide. Okay, the same question, you can see that now you have an exponent, and I will guide you and advise you to do this. Please, anytime you have any expression of this sort that has a negative exponent, and you are asked to differentiate from the first principle or what have you, bring it down. So it means what I have here is the same as x 3 plus x cubed all over x. Do you agree? Hello, I hope you agree. So this question here is the same as, okay, this particular question, but put in another form. It's the same as this question. Okay, it's the same. So work with a single fraction, and okay, after that, if you have to take any denominator x to a certain power up to make it numerator and you negate, you negate. So you take it to the form that the function came, and that will be it. Okay, so I think at this point, we'll come, okay, go for our water break. When we come back, we'll come and look at what's the rules, okay, of differentiation. So differentiation from the second principle, sort of. Okay, all right. So let me pause. You have your water break. Okay, so welcome back from the water break. Okay, so now we are going to look at how to differentiate functions, okay, using the differentiation rules. Okay, so you need to know the basic rules of differentiation, and it's not difficult at all. Okay, all the other rules that will come subsequently after this, okay, it will need, or you make use of these basic, okay, rules there. All right. So now let's look at the first rule, what we call the constant rule. Okay, so you know d dx, this is the operator. So it means we are assuming all the functions here, okay, will be in what, x, or all our functions that we have there will depend on x, so that we can differentiate with respect to that variable. So the x that you have here will tell you the variable that your function that you are differentiating, okay, contains, or indirectly, it will tell you the variable that you are differentiating with respect to. Okay, so now this is what we have. d dx of c is a constant. If you differentiate a constant, okay, you get 0 always. So if I have y to be equal to -5, then I have to take d dx of what? Of y, which will give me dy dx, and that will be equal to d dx of -5. Anytime I differentiate, okay, a constant, I will get what? What do you call it? 0. So that gives you 0. We have here as what? An example, an illustrative example. Point well made. So take it, anytime you differentiate what? A constant, irrespective of the variable that you are differentiating with respect to, it will always give you 0. Now let's come to what we call the power rule. And this one, okay, we'll be using it, okay, often. Okay, so anytime you have x to the power n, and you are differentiating with respect to x, this is all that you need to do. Okay, bring the original power down. Okay, bring the power down. Then the new exponent of your variable will be the power, the original power reduced by 1. Okay, so bring the power down, reduce the power by 1. Power down, reduce the power by 1. Is that clear? Okay, so that's how come you have this. Okay, so this is the general one. Now, particular, if I have x to the power 5, okay, then if I'm differentiating the rule, okay, I've been given y is equal to what? Okay, x to the power 5. So I'm taking d dx of what? Of y, and that should be equal to d dx of what? X to the power 5. Okay, so d dx of x will give me dy dx. By any time my operator is affecting a function to a certain power, what do? I bring the power down, keep my variable, okay, then reduce the power by 1. So it will be 5 minus 1. But usually when you are reducing, you don't write. You can add, you can subtract mentally. So that's what you do. So in effect, we are going to get this to be equal to 5x to the power 4. Okay, and that's exactly what you have. All correct. Hello, is my point well made? Okay, so now the constant multiple rule. You can see that what we have here, okay, is more or less a particular form of the power rule here is a particular form of what? Of the constant multiple rule. Okay, and this is it. With this one, okay, you can see that the coefficient of what? Your x here is 1. And your coefficient of your x can be any other value. So this is a special situation. So if your coefficient is not 1 and it's any other value, then this will be the constant. So that's why it's a constant multiple rule. So it's the same thing. Bring the power down. And in this case, the power will come down and multiply the constant. So it's like you keep your constant minus 5. Then you treat this one, the s squared, as what this. So that will give you, bring the power down, it gives you x, reduce the power by 1. So you get x. So that gives you, you now come and multiply minus 10 what? X. Point well made. Hello, is my point well made? My professors, are you there? Okay.
Yes, sir.
All right. Okay, so because you have done, okay, it already, I want another voice. Okay. So, please, are you fine, Daisy? Prof. Daisy, are you fine? Prof. Daisy, are you fine? Prof. Daniel, are you fine?
Yes.
Okay, all right. So then let me move on to the sum, okay, rule. Okay, so here you can see, okay, the sum of two functions, f of x and g of x, and you are differentiating these two functions, okay, with respect to x. So it's d dx of this, so you know your operator. Okay, so in actual fact, this is what you are supposed to have, okay, over there. So let me clear this then, create room for whatever I want to write. Okay, so this is it. Okay, so anytime you have, okay, sum of two functions, so in actual fact, this is the rule, d dx of what we said, you have f of x plus g of x. So I'm using sum of two functions, by extension, more than 2. So if you get the 2, you can extend it to. Okay, so this will be equal to, you differentiate term by term, so it will be d dx, okay, of your f of x, then plus d dx, okay, of what? Your g of x. But we know that if you find d dx, okay, when I was introducing you to the concept of differentiation and therefore the first principle, I told you that if you have d dx of what? Y, that will give us what? What's the best way to write this? That gives us dy dx. Okay. Then I told you that if you have d dx, okay, of f of x, this will give us what? Even today we've used it. That will give us okay, f prime of x. It will not be df of x dx, it will be f prime of x. That's the notation. So if I differentiate this, will give me f prime of x. Okay, plus if I differentiate this, that will give me g prime of x. Okay, so the differential of sum is the sum of the differentials. That's the meaning. The differential of sum of functions, okay, is the sum of the differentials of the functions. Differential of sum is the sum of the differentials. You get it? And it's the same concept for the difference. Okay, so the differential of difference of functions is what will always be the difference of what? Of the differentials. So take note. All right. So now, okay, if you get this, I think illustrative examples here. This one, if you are differentiating, you differentiate term by term. So if I differentiate this, I will use the constant power rule or constant multiple rule. So this will come down, give me minus 10, exponent reduced by 1, so 10x. This will come down, okay, I will differentiate term-wise. So 12, then x, you reduce the exponent by 1, so 2. So that gives us what you have here. The same explanation for this, only that the sign here that will change. That will be minus. So 10, this will also come down 10, but the exponent here will be 1. Okay, it will be 4 when you reduced. All correct. Okay, so this is just, okay, more or less the prelim. So now let's go and look at what the, okay, actual what rules. Okay, the more complex, okay, rules. Okay, what we call the product rule. So you use the product rule when you see the function that you are differentiating, you are dealing with what the product of what function. So if I have the product of two functions, f of x and what g of x, so you can see there's f of x times g of x. That's what you have there. So if I'm differentiating, this is what you do. Okay, you hold the first function, differentiate the second function. Okay, then plus you come and hold. Okay, you swap. Okay, but you can see that in what you have here, it is rather the first function that was differentiated, the second function held, then plus the swap. So this time around, you hold the first function, then differentiate the second function. But because multiplication is commutative, I said it this way. And in some books, you see it like that too, usually. So this can come here. So I said, hold the first function, differentiate the second function, come and hold what? The second function and differentiate the first function. Is the same. Okay, so illustrative example. Assuming I have this. So then if I have y to be equal to maybe x into x, okay, squared plus 1. This is what I have. Okay, so obviously you can see products of two functions. One of my functions here is x, so it's like f of x here is x. Okay, and the other function is x squared plus 1, so it's like g of x is what? Is what? X squared plus 1. Okay, so once you have this, when you are differentiating and you want to use the product rule, then I know I can say that then, okay, d dx, okay, of y will be equal to, so I've taken d dx of this side. I have to come and take d dx of this side as well. So x squared plus 1. But d dx of y will give me dy dx. Okay, which should be equal to, okay, if I'm differentiating this, my operator is affecting product of two functions, so I have to use the product rule. Hold your first function, so I will hold my first function. Then come and find d dx of my second function, which is x squared plus 1. Then plus, hold your second function, which is x squared plus 1. Because it's a binomial, anytime you are holding it, okay, or you have to put it in brackets. Then times differentiate, okay, your first, okay, function, which is x, so it will be d dx of x. Is my point well made, or should come again? This is the foundation. Make sure you get it. Okay, if you don't get it, I can assure you, you will struggle, okay, going forward. Okay, so we said, anytime you are differentiating, okay, let us know your differential operator. Okay, it will tell you if the nature of the function that you are differentiating or your operator is affected. If it is sum, difference, what have you, we know the rules. Okay, now we are talking about the rule for product. So I can see that my operator here, because I am differentiating with respect to x, it's like I'll find d dx of y. It's an equation. Whatever I do here, I have to come and do same here. So d dx of the whole of this, which is the same as your y. So d dx of y will give us dy dx. And very soon you know why I will always want you to write the operator, know the operator. Okay, very soon. Okay, even at this point, you can see it is very useful. So my operator is affecting which type of function, product of function. But the rule says, okay, I hold the first function. So my first function is x. Then differentiate my second function. But anytime I'm differentiating, I should know my differential operator. So it will be d dx of this. So meaning I'm differentiating this function. Is that clear? Once my operator is before it. Then plus hold your second function, then differentiate the first function. So once I'm going to differentiate the first function, my operator can d dx of this. So meaning this will tell me that I'm differentiating this function. Is that clear? So what I have there is basically for explanation purposes. So this will now be equal. The person who said, we're not okay, are you okay now? Okay, so now what do? We are going to hold the first function, then you are going to differentiate. And you can see that your operator is affecting sum of functions. So you have to use the sum rule. And the sum rule, we said we differentiate term by term. So it means I'm going to get, okay, times the differential of this, which will give me 2x and plus 0. I will write because the differential of constant, okay, will give me 0. Then plus, I hold my s squared plus 1. Then come and differentiate the x. If I differentiate the x, you know, the power here is 1. It will come down. I will come and get 1. Then it will be s to the power 0. So that will give me 1. So anytime you differentiate x, you always get 1. Anytime you differentiate a constant, you get 0. So take note. So at this point, you are more than good to go. You remove the bracket 2s squared. Then this will give you plus what? Okay, s squared and plus 1, which in effect will give you 3s squared, okay, plus 1. So that will be the differential. And okay, again, okay, I wanted to say, and I will say that because the function came in the factorized form, if your result you can factorize, you factorize, but here you can't factorize, so you end here. Point well made. This is just the illustrative example. We'll use this formula, okay, going forward, okay, a lot. So let's go to the chain, or the quotient rule. We'll come to the chain of composite. So the quotient rule, this time around, you know, products, multiplication, quotient, division. Okay, so anytime I'm differentiating a function over another function, I use what we call the quotient rule. And this is what the quotient rule says. Okay, this is what you do. Hold the denominator function. With this one, okay, you have to go by the rule strictly. Unlike the other one, because addition is commutative. And you saw with this one, okay, you saw that in what I have here, I said differentiate, hold. Okay, then the other one, hold, differentiate. Okay, but when I was doing mine, I said hold your first function, then differentiate your second function. But with this, it is differentiate and hold. But because addition is the same, I mean commutative, you get the same result. However, here, no. Okay, the other one, it doesn't really matter which function you hold first and differentiate. Okay, but this one, it is very critical. You hold your denominator function, differentiate your numerator function, then minus, hold your numerator function, differentiate the denominator function. But unfortunately, that's not all. All over the denominator function square. And all the rules here, we can prove it. But it's not necessary. I won't bore you with the proof. We just need to know the rules and how to apply or make use of it. That's all. So example. Okay, if I have maybe a function y is equal to, let me use, okay, x squared over maybe x plus 2. Okay, this is what I have. Obviously, you can see that your function y is a rational function, a function over another function. Okay, so quotient of functions, how do you differentiate? So this is what we are going to do. It will be d dx. So I'll write this then, or this implies that d dx of y will be equal to d dx, okay, of what we have here, which is s squared over x plus 2. So d dx of y will give us dy dx. As you mature, you can write it straight away. And that will be equal to, here my operator is affecting quotient of function. And we said anytime you are differentiating and your operator is affecting quotient, the rule is that hold the denominator function, which is s plus 2. Okay, differentiate the numerator function, so it will be d dx of the numerator function, which is s squared. Then minus, you swap, come and hold s squared, differentiate what's the denominator function, which is s plus 2. But unfortunately, that's not all over your denominator function, s plus 2, all squared. Point well made. Hello, is my point well made? Hello, my professors, are you there? Is my point well made?
Yes, please.
Okay, all right. So if that's the case, then I guess we can, okay, move on. Okay, so here, you know, the numerator, you can work on it. And again, my advice is never expand the denominator because it is already in its factorized form. So that if there is any reduction, okay, you can do so. So this one, you keep your x plus 2. Okay, differentiate the s squared. So this will be in bracket, which will give you 2x. Then minus s squared, differentiate s plus 2. The operator is affecting sum of functions. So what do? Here it was affecting power. So we use the power rule. This will come down x, reduce the exponent by 1. And here your operator is affecting sum. So you differentiate term by term. So we are going to get d dx of x, and that will give us 1. Then plus d dx of 2, that will give us what? Okay, 0, we don't write it. So in effect, if you continue, we are going to get, okay, therefore our dy dx, okay, to be equal to, if you expand, you get 2s squared minus or plus 4x, then minus s squared, okay, plus 1, all over. Don't expand your denominator, never. Okay, squared. So this in effect will give you, okay, s squared, okay, plus 4x, and plus 1 all over s plus 2 all squared. So you ask yourself, if this function that you have here, you can factorize, and obviously you can't factorize. Because factors of 1, you can't get such that will give you, okay, your results to be 4 if you sum. Point well made. Is my point well made, my professors?
Yes, please.
Okay, so at this point, we are more than good to go. I think, okay, we can, factorization will not be necessary because you can't factorize, you can't simplify. So that's how far you can go.
Sir,
Yes, please, I'm here.
please, can you factorize the first 2 terms and leave the last one out? Or it's
No,
not
when you
possible?
are doing factorization, okay, you don't factorize in terms of, if you want to factorize by grouping, if you group the first 2, you have to go and group the last 2. So factorization, anytime you are factorizing, okay, you should have brackets there. You shouldn't have a bracket and maybe plus anywhere. So if you factorize, you are going to get s plus what may be 4, okay, then plus 1. You have not factorized because you can see a term and a term. You don't see factors. Point well made. Okay, all right. So now let's see what we are supposed to get. Okay, I mean, going forward, the next rule. Okay, so I've done the quotient rule. Okay, I wanted to give. Okay, so let's look at, okay, this particular one. Okay, when we deal with it, then after that, I'll introduce you to the last one, which is the chain rule. Okay, so we'll do the chain rule in our next meeting. So let's look at the following question and how to make use of all the rules that we've learned so far. Okay. All right, so quickly, we have some few minutes left. Okay, so differentiation, okay, so 1, you are supposed to differentiate the following functions with respect to x. So it means our operator is d dx. We are differentiating with respect to x. So a, 1a, we've been given f of x is equal to minus 3x to the power minus 7. So you are differentiating. So I'll write, this implies that our operator is d dx of f prime or f of x, sorry, will be equal to d dx, okay, of what? Minus 3x to the power negative 7. So d dx of this will give me, so therefore f prime of x, okay, will be equal to, if I differentiate this, I'm going to use power then multiple, okay, so constant multiple. So we have, okay, minus 3, so this will come down, minus 7 times minus 3, and that will give us positive 21. Okay, keep your x, reduce the exponent by 1, so it will be minus 7 minus 1. So that will give us minus 8. Okay, so this gives you your result. Is my point well made? Hello, is my point well made?
Yes, please.
Okay, so the next one, what are we supposed? We are given y. So look at the presentation. So given y is equal to what? Okay, x to the power 2 on 3. Okay, no issues. Your power is not that pretty. The rule is the same. So this implies that d dx of y, because you are differentiating with respect to y, you need to know your operator. So with respect to x, you need to know your operator. So, okay, I've indicated our operator. So here, d dx of y will give you dy dx. Okay, as you mature this one, you write it. Okay, so now bring the power down. So that will give you 2 on 3. Keep the variable, reduce the exponent by 1. So it will be 2 on 3 minus 1, and that will give us okay, so I'm waiting. Oh, hurry up. I've told you I don't do these calculations.
-1/3.
Okay, so negative 1 on 3. Okay, so this then becomes your answer. Okay, so any questions?
No, please.
Okay, so you do same for whatever you have here. Only that is the what do you call it? This particular one that you have to. So anytime you are differentiating and the exponent of your x is not explicit, okay, make sure it is explicit. So it means here, what we are giving there, which is your f of x, is equal to 4 root of x. You rather write this one as 4 root of x is the same as 1 x to the power 1 over 2. So make sure the exponent is explicit before, because the differentiation, you need the exponent because you work on the exponent. You get it?
Yes, please.
Okay, so we can move on to our next question. Okay, so now what do we have? We move on to the next question. Okay, so differentiate the following with respect to x. Okay, so let me see whether probably you will be caught in the web. Okay, what will be your approach in differentiating this function, especially the first one? Let's start with the first one. Prof. Kobe.
Okay, so first of all, I'll change the function, which is y on 3x. Y is equal to 3 on x2. Y is equal to 3x exponent -1. And
Okay,
I
that's it.
differentiate
It's
from
okay.
there.
It's okay. All right. So you have that's clue. So please take note. Anytime you are differentiating and you see quotient, okay, the fact that you see quotient doesn't mean go and flex your muscles with the quotient rule. Okay, quotient rule, the chain rule, the product rule. If you can avoid, avoid. Okay, and I'll let you know when, okay, or the situation that you can avoid using these, okay, rules. So with this one, it's quotient. You see a function over another function. Okay, however, anytime you are given such a situation, okay, and you realize that your denominator contains a monomial, and it's the monomial that contains what the x. Okay, it means you can always avoid. So take it up, your x up, and when you take it up, you know how to deal with the exponent. So it means in this case, you have to transform your y before you start dealing with it. So given, okay, y is equal to what? 3 over x. I know working with it directly, okay, I will need a quotient rule, but I want to avoid because the rule itself, okay, putting it will take your time, and writing it as well, in terms of you even substituting, will take your time. It will not be ideal. So unless you are restricted, don't use it, okay, if you can avoid. So this will give us 3x to the power negative 1, like he said. So now it is this function that you want to differentiate, all right? Therefore, dy, dx are matured. I know this will be equal to, I bring the power down, that will give me minus 3. Keep the exponent variable, reduce the exponent by 1, minus 2. But you have to be careful. After transforming, remember you've seen so far, even from the first principle, anytime you transform the given function, okay, it behoves on you to equally transform your results to meet, okay, the form of the. So you can see that with this one, you have a numerator and a denominator. The x didn't have a negative power. So you take it back to the form. So this will be equal to, keep your minus 3, bring the s down, and the exponent becomes 2. Is that clear? So you can see that your differential, okay, is in the form, or the same form as what? Your given function, the same form. Take note of that. Okay, so that's exactly what you do in these situations as well, the rest. Is my point well made, my professors?
Yes, please.
Okay, so let me, if that's the case, then I can move on to our next set of questions. Okay, so with this one, obviously we can see. Okay, so let's look at what we have there. Okay, more than a term, unlike the previous ones. Okay, we're dealing with terms, even if it's a fraction, it's just a single term fraction. Okay, so when you are differentiating, you differentiate term by term. Okay, so a combination of addition and subtraction. So I will do maybe the B, come and do the C, and as a guide, you use it to do the rest. Okay, and maybe we'll end, okay, here. So let's go and look at the solution. So solution to question 3. Okay, I won't do the A, I will do the B. B, what are we giving? F of x is equal to what? 4x cubed minus what? X squared plus 2x then minus 1. So I'm differentiating, so I'll write, okay, I'll maybe write, this implies that d dx of f of x will be equal to d dx of the whole of what? 4s cubed. And I always want you to indicate your operator. It's very important, especially when you know this. Okay, dealing with the implicit function differentiation, your work will be very easy. Okay, so at this point, I know d dx of f of s will give me f prime of x, which is what I've been asked to find anyway. So if I differentiate with respect to x, I will get f prime of x. So now your operator is affecting terms, okay, or some differences of what function. So you differentiate term by term. Okay, term by term, take note. So if I'm going to differentiate the first term, okay, I will use the constant, okay, multiple rule. So I bring the power down, we are experts now, so that will give me 12. X, reduce the exponent by 1 squared. Okay, bring the power down, minus 2, reduce the exponent by 1, so 1. Then plus, okay, there is 1 here, bring it down 2. Then you get s to the power 0. Okay, so that will give you 1. The differential of this constant here will give you 0. You don't write it. So we are done. All correct. Is my point well made?
Yes.
Okay, so I'm going to do the C. Okay, like I said. So C, what are we giving? Y is equal to, okay, 3x squared plus 7x, okay, minus 4 and plus 1 over x. Okay, but take note, okay, this needs a little transformation. Okay, anytime you have a fraction and in that fraction, you see one term, okay, variable, a variable term, monomial, and you know, take it to bring it up. Other than that, when you are differentiating term by term, you have to use the quotient rule. So differentiating this term, I can avoid the quotient. So I'll write this equal to 3x squared plus 7x. I haven't differentiated though. I'm transforming it. Okay, 4 then plus s to the power negative 1. Do you agree? So now I don't have any denominators for quotient root to come in. So I will have, therefore, my dy dx will be equal to ddx will affect, I will differentiate term by term. So it will give me 6x plus 7 minus what? Okay, this will give me 0. So if I come this, I'll bring this one down, minus 1. I will write it simply understood to be there, then x to the power negative 2. Do you agree? Are you with me, my professors? Okay, however, I cannot end here. Remember, okay, the question didn't give me a negative exponent. So I avoid concluding with a negative exponent too. So that will give me 1 over x squared. So this then becomes your final answer. Take note. Always use the form as a guide. So at this point, we are going to end here. Okay, now next meeting, we'll look at more complex questions. Okay, we'll bring the curtains down on differentiation, especially the rules. Once you get the rules, as for the application, okay, when you read, you can get it. Okay, all right, so thank you very much. Okay, please take care, have a wonderful day. Okay, so bye-bye.